P of NH3, let's put it in a parenthesis. What'd you raise it to the power of? 2, just like before. What do we put on the bottom? P of N2, put it in parentheses, raise it to what power? 1. And then last but not least is what?
H2.
Okay. P of H2 raised to what power? 3. Not bad, right? Okay. All right. Now, I told you earlier that the only thing that can change a K is a temperature, a change in temperature. So what you'll notice is if you're ever given K values, they'll specify the temperature. So I was looking up in the book some values for these. At 300 degrees, the Kc value is 9.6 and the Kp value is 4.3 times 10 to the negative 3. Okay? And the one thing that I want you to notice is the numbers are indeed different. But didn't we say earlier that concentration, moles per liter, and pressure are not going to be the exact same number, right? Okay? In fact, there's actually a formula that you can use to convert from one type of K to the other type of K if you have gases. And it is Kp equals Kc times RT to the delta N. Okay? Do you see where they're getting the RT factor? And I want you to know that delta N just refers to the difference in your moles of product versus reactant. How many total moles of product do we have here? 2. How many total moles of reactant do we have here? 4. So 2 minus 4 is negative 2. So you'd put a negative 2 here, you'd use your 0.0821, and you'd convert your temperature to Kelvin. Now, this is a calculation we used to have to do on the AP exam, and it was given on the green sheet. They no longer have that formula on the green sheet, and they no longer require this calculation. I wanted to expose you to it so that if you see it in college, you know how to do it. If you see it in the book, or if you see it in an old, like AP Chem test prep book, okay, that you won't freak out that, oh, Mr. Crawford teaches this, okay? It's just something that we no longer have to calculate. But if you were given the formula, you guys would be just fine, right? Okay, so, but what I'd like to do is I'd like for us to talk about, just in general, the concept of K. When you see Ks that are small, okay, do those favor reactants or products if the K is small? Why do you say reactants? You're right. Where are reactants? In the denominator. So if your denominator is bigger than your numerator, you're going to get a number that's less than 1. So in general, K values less than 1 favor reactants, and K values that are greater than 1 favor products. Although I will say, like this, 9.6, that's really not a huge number. I mean, there are some equilibrium constants that are 9 times 10 to the 8th. I mean, they're really big, okay? So for that reason, we kind of say if they're a lot less than 1 or a lot greater than 1, then you can tell if it favors reactants or products. If it's kind of close to 1, it's actually kind of hard to tell, okay? Does that make sense? Okay. Now, what's interesting about this reaction is this reaction actually helped turn the tide of, I think it's World War I, okay? NH3, ammonia, is really important in the production of fertilizers. So you can help feed the world, okay? Unfortunately, it's also used in ammunition. So then you got the other side, okay? But they were trying to find ways to produce NH3, and if you look at the K value, it's not really big. So the chemical engineers, the chemists at the time, had to figure out conditions they could change to force the reaction to go further to the right, okay? So they used something called Le Chatelier's principle, which is what you'll be reading about tonight when you read over your lab. You don't need to do anything except for, I don't want the first time that you are reading through the lab to be tomorrow in lab, okay? So I just want you to read through it so that you're familiar with it. We'll talk about it and kind of decode it tomorrow, but it's a way that we can use to help equilibrium reactions shift more in the direction we want. Does that make sense? Okay.